Okay, so today we'll talk about diffusion maps. Okay, the idea is given a graph, right? So we take a graph with vertices, edges, and weights. And the idea is to represent this graph in Euclidean space. So we're going to take the graph G, right, its vertices, and we'll like a map that takes the vertices into RD. Right? You can think of this as a goal of embedding the graph in Euclidean space, of visualizing the graph. And we'll do this through diffusion maps. Right, so the goal is to build some map, say phi, that takes the vertices into RD and somehow captures the structure of the graph. Now, there's already been some hints of that this may be possible in some ways, right? Because remember what we did in spectral clustering. In spectral clustering, we took the vertices of our graph, and then we took the values of their eigenvectors of these phi's, and then we said that by the time we take this map, then even k-means should be able to cluster the graph very well. So in particular, what this is hinting at is that somehow this map that was used before we did a spectral clustering, before we did k-means on the spectral clustering step, is already sort of opens up the graph and makes the cluster show up in different places, right? Which is a bit like it's opening up the geometry of the graph. And in particular, it doesn't actually need to come from a graph, right? We might have some type of twisted manifold, right? We might have some data set that looks like this. Let's say we have something that looks like this, right? Where naturally the two clusters that we would like here, right, as we saw when we talked about clustering, maybe these are the right clusters. Right, but k-means will never find this. Right, k-means will never succeed at finding these clusters. But maybe we can go from here and build a graph. Right, we can build a graph. Right, the graph can be built maybe by some kind of kernel. Right, as we saw. So things that are nearby, we connect them. Right, maybe this gets connected too. Right, but maybe this is connected. Maybe there's some connection here and so on. But now, if you look at this graph, there's very few connections across and lots of connections within. And we can even capture this with the weights, right? The idea is to build a graph where, right, so going from point cloud or data set, so going from point cloud or some data set of some type, right, to a graph, we can do this via kernels, right? So the way we can do this is we can take, well, node point, right? So we have points x1, xn. I mean, right? We did this for spectral clustering as well. And now we build a graph, right? So we build a graph G on n nodes, where the weights that we take are going to be given by some kind of kernel between where, right? The weight is very big if the points are very close to each other, right? So one possibility is to do, say, the weight wij will be given, say, some kind of exponential, say, minus xi minus xj squared over epsilon. Right? It's one possibility. But in general, it will be some kernel, depending on epsilon, which is sort of the scale of your problem, of, say, some norm of xi minus xj. Right, and this is the Gaussian kernel in this case, but you can have other kernels. The idea being that, right, because of this scaling, here you're only going to get points that are at a distance square root epsilon. Right, if something is at a distance much bigger than square root epsilon, then you're never going to see it. Right, because if something is at a distance much bigger than square root epsilon, then this will be exponential of minus something very small. And so you won't see it, right? So these distances will be very small, and these ones will be on the scale of 1, right? And so effectively you're capturing something like this, and then we have a graph. We knew we could cluster, but maybe what we're going to do here is we're going to visualize now this graph. So we're even going to be able to take in something twisted like this, right? Build a graph. And then from the graph, project it this way, maybe to something that actually entangles the surface, entangles this manifold, right? So this will be our goal. Okay, but so the idea of diffusion maps will turn out to be exactly to exploit this map that we derived for spectral clustering. But we'll do this one step at a time. So we'll need to, the idea sort of on the technical side is to consider diffusion on the graph, like heat equation or like diffusing of a chemical or some random walk. And we'll consider diffusion starting at, say, a point here, and a point, say, here, and say a point here. So think about the experiment where you put some chemical or heat or a random walker and you look at the probability cloud right at this point, and now you let it evolve, right? So the chemical will spread everywhere, and will spread more here, and maybe a bit of it will be here, and will go here, and so on. Now you do the same thing here, and you do the same thing there. And now you want you want to consider that 2 points are nearby in sort of their intrinsic geometry. If the heat profile or the random walk probability cloud or the chemical concentration profile of them are similar, right? So this will be the key idea. Okay, but let's start writing some expressions. So we're going to define a random walk, right? So we'll define a random walk, right, on the graph, on G, but in particular on the vertices of the graph. Right, and so this random walk will be defined the following way. The probability, right, so x is the position of the random walker at time t plus 1, right? The probability that he goes to a node j, given that he was on a node I in the time before, right, will be proportional to the weight. Wij. Of course, the probabilities need to sum to 1, right? It's coming out of I. The probabilities of everywhere it could go need to sum to 1. So this, you divide this by degree of 1. Right? So this is the distributions of the random walk. And now we're going to take the matrix M. We're going to define a matrix M, the matrix of these probabilities. Right? Matrix of these probabilities. Okay, so Mij is exactly this matrix, right? So this will be exactly Mij. Okay, now M we can write it quite nicely, right? In particular, I mean, let's first do some properties of M. So Mij is always bigger or equal than 0. Right? I mean, it's some weight, it's a probability, it's some weight, or it's a negative number divided by positive number. There's no isolated node, let's assume. And Mij is bigger than 0, right? Because it's a probability, right? Because it's a matrix of probabilities, the sum over the rows is for sure 1. So M times the whole one's vector is equal to 1. Right? And it's easy to write M in terms of the weights, right? M is just the matrix of the weights, where we divide each row by the degree of the vertex associated with that row. And so we have that we can write M very neatly as d minus 1 doubles, right? Where this is the matrix, diagonal matrix of degrees. Okay. So now we're gonna use this matrix M to study this diffusion, and we're gonna then, motivated by the diffusion, we're gonna come up with an embedding of the vertices of the graph in RD, and it will be a very good way of actually visualizing a graph. All right, but now before I do that, I just want to show a connection, a very interesting connection with normalized cut. At some point I said when we mentioned normalized cut that normalized cut will be related to probability of jumping in a certain random walk, and the random walk is exactly that. So there is a proposition one can prove, right? So I will not prove it here, but this is a very nice homework problem, right? So I encourage you to try and do it, right? So maybe I'll switch pens. Okay, so the proposition is the following. Given a set S, inside the vertices, the normalized cut of S is exactly the probability of jumping from S to S complement plus the probability of jumping from S complement to S, right? So the probability of condition you're in S jumping to S complement plus the probability of condition that you are in S complement jumping to S. Okay, so then normalized cut of S is exactly the following. The probability that X at time t plus 1 is in S conditioned on X in the time before being in S complement plus probability xt plus 1 being in S complement provided that xt was in S. Right, so there's a very nice interpretation of what normalized cut in terms of probabilities. Of course, this depends on the original probability that I'm considering for xt, right? Where the xt, right? So in order to talk about the probability of jumping, being somewhere, conditional on being something else, somewhere else, and so on, I need to tell you what is the probability of xt, and it will just be the probability, the uniform probability over the nodes, weighted by the degree, right? So where probability of xt being a node I will be just equal to the degree of I divided by the sum of all the degrees, which we call the volume of the graph. Right, so this is a very nice connection between the normalized cut and this random walk that we just defined. M is what's called the matrix of transition probabilities, right? So M tells you what's the probability of transitioning from I to J. That's what the entry Mij tells you. Now, it's not hard to see. I mean, if you've seen some market chains before, you know that, right? If you want to see what's the transition probability after 2 steps, right? Not just taking 1 step, but I let the random walker take 2 steps, then this transition probability is just M squared, right? Because the probability of jumping in 2 steps from I to K is the sum over all J of the probability of going from I to J and J to K, and this is exactly matrix multiplication. Right, so if you've seen some market chains before, you will have seen this. Otherwise, I recommend just trying to work this out as a homework problem. Right, and so we know in particular that, you know, it's not hard to see that for any t bigger than 0, a constant integer, that the probability, right, that you are at time t in J, conditioned on being, right, or assuming that you start at I in 0, right? So after t steps, so for 2 steps would be M squared. Of course, if you just continue doing this for t steps, this is just M to the t, right? So this is just M to the t entry Ij. Right, so this is a basic fact on market chains. If you have not seen market chains, I recommend you just work this out as a homework problem. This is a very nice set of calculations. So in particular, it means that the probability cloud right, the probability cloud of if you start at I and you run t steps, right, and you want to know after t steps what are the different probabilities, right, of being in the different nodes J, right? We'll call this the probability cloud. Maybe it's 10% of being the first node, 5% of being the second, and so on. This is, right, the probability cloud of xt, right, indexed by there's now will be a vector for each value J will be a value of this vector. Assuming that you start at I, right, this is just MT, right? In MATLAB notation, this is just the first row, right? And all that. This is now a vector, a line, a row, and it will just take the ith row of this matrix MT. Right. Another way to write this is that EI transpose MT. right? Where EI transpose is just a vector, this is just a vector with a 1 in entry Y and 0 everywhere else. So if we're thinking in terms of how we're going to have this diffusion, like this map, this embedding, going from a point to a vector space, to just our D to D numbers, and it will depend on what the probability cloud is doing. It will depend on what the probability cloud is doing after a bunch of steps. So what the diffusion, right? The diffusion, the heat profile, the chemical concentration profile. What does it look like after a certain number of steps? Then a natural map, right? A natural representation is just to take node I and represent node I into exactly this vector. Right? This would be a natural representation. So for each point I, we put it in a vector that corresponds to the probability cloud, the values of the probability cloud at all the other points. Right? It's exactly this idea that if 2 points after t steps, the probability of, if we start random walkers at 2 different points, and after t steps, the probability cloud looks very similar, that these points should look similar, and therefore you should represent them nearby or similarly, then this would be a very natural representation. Now, what are potential problems? So potential problems are, first of all, this has n vectors, so we're going to take dimension d to be n, right? This is a problem because, right, n is very large, is the number of nodes. We don't want to have the dimension equal to the number of nodes. Right? Also, I mean, there's another thing which was only using, right, because all these numbers are between 0 and 1, they're all adding up to 1 and so on, so we're using sort of a strange part of the space. We're not using all of the space. We're just, it seems like we're using a sort of a strange part of the space, and so we want to distribute the points a bit more nicely, but main issue is that really, right, we don't want the dimension to be equal to the number of nodes. Okay, so we're going to use some, spectral theory, just like how we've been doing, to try to remedy this and try to alleviate this issue. Right now we would like to, it's much nicer to do spectral theory and to use eigenvalues and eigenvectors of symmetric matrices. Now, M is not symmetric, of course. I mean, unless the degrees are all the same, right? Unless it's a so-called regular graph. Now, when we were talking about PageRank, this wasn't an issue. It still did a lot, even though the matrices involved weren't symmetric. But here, this matrix, although it's not symmetric, W is symmetric, right? And this will be very important. We're going to really exploit the fact that W is symmetric. Remember that in PageRank, this wasn't the case, right? Because here, the random walk matrix itself is not symmetric, but the underlying graph is an undirected graph. While for PageRank, it wasn't. Just because page A links to page B does not mean that page B links to page A. Okay, so let's... I'm going to leave this natural representation here. Okay, so M is not symmetric. Right, so we know that. So M is not a symmetric matrix. However, it's almost symmetric in a certain way, right? So M is equal to D minus 1 W, and W is symmetric. And so we're going to take a matrix that shares the spectrum with M and that is symmetric. Right? Remember in PageRank we did something similar. We took the transpose, it wasn't symmetric of course, but we knew something about its spectrum. We're going to do exactly the same. Here, if we're going to take another matrix, in this case it'll be symmetric, so we'll know a lot about its spectrum. The spectrum symmetric matrix are a lot nicer, and the spectrum will be the same. Right? And so we'll take a similar matrix, right, in the sense of linear algebra, and we'll take S equals to And now we're just going to make this symmetric. So we just take d to half, m, d to the minus half, right? So we're hitting it with the matrix and then with the inverse on the other side. So this shares as the same eigenvalues. Right, and now S given in terms of W is just d to the minus half W d to the minus half. Okay. But remember, okay, so the Laplacian is sort of showing up here already, right? Because remember that the Laplacian was d minus W. And the normalized Laplacian was, right, you take a d to the minus a half on both sides. Right, so this is identity minus d to the minus a half W, d to the minus a half. Oh, this is typo. It's supposed to be an L. Right? This is when d to the minus a half hits here on both sides, you get identity. When it hits W, you get S. Right? So S and the normalized Laplacian are very related. In particular, they have the same eigenvectors, right? Because taking a minus sign does not change the eigenvectors, and adding identity also doesn't change the eigenvectors, only the eigenvalues. Right? This will also be important. Okay, so now because S is symmetric, right? Because S is symmetric, we can take its spectral decomposition. Right, we're going to take its spectral decomposition. And so S is going to be equal to V, big lambda V transpose, right? Where V transpose V will be identity, right? And by identities, of course, right? They'll be the eigenvectors. And lambda will be a diagonal matrix, where lambda kk is just a kth eigenvalue, right, of S. Right, we'll just often use this as just lambda k, and we'll take away, we won't put the S, in. Now, these eigenvalues are of course related to the eigenvalues of the Laplacian, right? The eigenvalues of the Laplacian will just be 1 minus that. And we order the eigenvalues of the Laplacian from the smallest to the biggest, right? So here it'll make a lot of sense to order from the biggest to the smallest, right? So we'll think of these eigenvalues now from the biggest to the smallest. And we'll oftentimes just not consider right? Just not use S. Right, and now let's give some more notation for everything. So V is the matrix of eigenvectors. Let's actually write them. V1, Vn. Right. Now, right, because the normalized Laplacian is just identity minus this matrix, these are also, right? These are also the eigenvectors of the normalized Laplacian, right? Just order it the other way. Moreover, right, the eigenvalues of the normalized Laplacian, right, are simply 1 minus these eigenvalues. Right? And of course, when I say these eigenvalues, I mean with of S. Right? I'm just going to start, not showing always when S shows up, and when we say lambda k, we mean it in this lecture always of the eigenvalues of S. Okay, and of course we have, right? I mean, by definition, right? We have S Vk is of course equal to lambda k Vk. Right, but now we can use this. We can use this decomposition to come up with a decomposition of M. Right, so let's save the stuff that we need. Let's see. Okay, so let's save some of the things we need. Let's say m is equal to d to minus 1w. S is equal to d to the 1/2 md minus 1/2. And we also have that S is equal to V lambda V transpose, right? So for now, these are the things that we're going to need. Okay, and then maybe I should write here too, V1 all the way to Vn, right? These are just the columns, and the kth eigenvalue we're calling lambda k. Okay, right, so now we can erase this. Okay, so now from this, we can actually come up with a decomposition for M too, right? Because what is M? Right, M is equal to, right, I mean, we have to now redo this, right? So it's equal to d to the minus half, S d to the half, right? If I hit d to the minus half on this side, d to the half here, I just get M on this side. So what do I have? I have d to the minus half V lambda d to the half V. Oh, the V should be on the other side. Okay. And then V transpose d to the half. Right, but now I can rewrite this even a bit better. I can just say d to the minus half V. And I know that these are also the eigenvalues of M, right? Because M and S are similar. Right? When I take the transpose here, I get V transpose, and then I get D to the half transpose, but since it's a diagonal matrix, nothing happens, right? It's just exactly the same thing. Right, and now we're going to give definite, we're going to call these matrices new things. So this will be the matrix phi, and this will be the matrix psi. Capitals. Right, so we'll have these matrices phi and psi, and they will have the left and right eigenvectors of M. Right, so in particular, let's give this name some more notation. So this will have columns phi1 through phi n, and this will have columns psi1 through psi n. Okay, and so what we have is we have that M, and so we have that M is equal to phi, right? This should be, right? I mean the matrix inside, maybe let me make this more precise by putting here a transpose. Actually, let's think better if I just do, right? It's just what's inside the parentheses. Right, so we have phi, the matrix phi, times the matrix of eigenvalues, times the psi transpose. Right. Now, these phi and psi, right, they're not a spectral decomposition in the sense of symmetric matrices, but they form a so-called biorthogonal system. Okay, what do I mean by this? I mean that if I take phi transpose psi, right, then what happens, I get phi transpose, I get V transpose, d to the minus a half transpose, then it hits d to the half, that these disappear, and it hits V. So it's V transpose V, this is just identity. And of course the same thing happens on the other side, exactly for the same reason. Right, this is just identity. So in particular, I mean, it's exactly the similar product. So in particular, this means it means that phi I psi j and the inner product between phi I and psi j is equal to the delta of I and j. Right? right? So this is 1 if I is the same as j, and 0 otherwise. So we know that this is a bi-orthogonal system, right? The inner products give 1 if they are the same, and 0 otherwise, right? If phi was the same as psi, this would be exactly the same as being an orthogonal system. This is called a bi-orthogonal system. And in particular, what this immediately gives is that these are, respectively, the right and the left eigenvectors of M, right? So what do we mean by this? If we take M and we hit it with phi k, right? Then phi k will hit a bunch of the psi's, but only psi k will survive. Only the row corresponding to psi k will survive. We'll get a what? We'll pick up lambda k, and then we'll show up phi k again, right? So this is lambda k, phi k, and psi k is just right, the left eigenvector. Right, so these is actually the right and left eigenvectors of them. So in particular, we now have, this spectral decomposition allows us to do the representation in a different way, right? We can rewrite this decomposition. Okay, so let me do it here, right? So we can rewrite this decomposition in the following way, right? Just like how we usually do with spectral decompositions. Okay, from 1 to n, right? So lambda k, phi k, psi k, right? So this could be this is one potential decomposition that we can write. And in particular, the nice thing of this decomposition, so let's go. Nice thing is if I now take, m to the t, then of course, right, if I multiply this over and over again, only the cross terms all go away, right? Because if I take two different k's, and there'll be a phi k1 hitting a psi k2, and there'll be 0. So only the cross terms all go away, and so we have the m to the t, just like in normal spectral decompositions. This is just lambda kt psi k transpose. Right? And so, in particular, this immediately suggests an embedding, right? What we call the natural representation, or a suggested embedding, right? A suggested embedding, right? Just like in there, now can be written very nicely, right? Because the node I, right, it will just go to this expression, right? Let's say mt rho I, MATLAB notation. But now this is just the same thing as taking in this language. This is exactly the same thing, right? So the entry of this matrix ij is just you take phi ki psi kj. So this is exactly the same thing as just summing from 1 to n phi k times t psi k transpose. Right, so it's looking nicer. Now, of course, we can write it, right? This is very naturally written now, this decomposition in the psi k bases. Right, so now we can write decomposition in bases psi k transpose. Right? We can think of it as writing it in this phases, and in this phases the coordinates are the following. So if we do that, we get the node I, right, or sometimes called VI, right? We map to this vector, but in the coordinates of phi k transpose. So on the coordinates of the phi k, so it's just now these these numbers here, right? And so this would mean that you now have a decomposition that's simply given by lambda kt. 1 phi k sorry, phi 1 point I lambda 2 transpose phi 2 lambda 2 to the t phi 2 and I, and lambda n t by n. Right, and now this is a very natural decomposition. Right, it's a very natural embedding. It's exactly the same embedding that we had before. Right, just now written in the basis of psi k. Now we know one of these eigenvalues, right? Because we know that m1 is equal to 1. So one of these eigenvalues is non-interesting, and in fact, this will be the first one. Right? We saw this already in page rank. Right? The first eigenvalue will be 1, and so in particular, right, the right eigenvector for m, phi 1, is just a Holland's vector. Right? And so we'll, we saw this already in spectral clustering, we saw it in page rank, but let's prove, just for here, there's a very, very simple proof that, in fact, all the eigenvalues are smaller or equal than 1. Right, so we can exploit the symmetry and here have a simple, very simple proof. So we'll see that all the eigenvalues in absolute value are smaller than 1, and there's one at 1 which is not interesting. So this will motivate us to consider the mapping where we just ignore the first one because, right, if all the nodes are going to the same point because this is the Holland's vector, then in just one dimension, the graph is being projected all in one point. There's nothing interesting going on. Right? Okay, so let's show that. Okay, so all the arrays now a lot. We don't need this anymore. Okay, so let's prove that all the eigenvalues are actually smaller or equal than 1. Right? So there's a very simple argument for this. So take now phi k, right, the associated eigenvector, right? And take I max, the entry such that phi k is the one that has the largest entry in absolute value, right? I max is largest. Maximum is largest. Okay, now we just need to see what's happening with this one, right? We know that lambda k, right, phi k, I max, right, is equal to, of course, m phi k, this matrix at entry I max. Right, but what is this? This is just the sum over j from 1 to n of m I max j phi k j. Right, but now by triangular inequality, right, by triangular inequality we have that I'll go over there, it's a bit easier to see. Right, so by triangular inequality, right, we have that phi k, of course, lambda k phi k I max, right, is equal to the absolute value of this sum. By triangular inequality, this is smaller or equal than the sum of the absolute values. I max j phi k j. Right, where, right, the absolute value here is equal to the absolute value of the sum. The absolute value of the sum is smaller or equal than the sum of the absolute values, and then I can put an absolute value on the product. Each one of them is all the same, right? So this will imply, right, I can do the same thing here, right? I can do this, nothing changed, right? So we have that lambda k, right, is for sure smaller or equal than the sum from j from 1 to n, right, of m I max j, now phi k j over phi k I max. Now, by definition of phi k I max, this here is smaller or equal than 1. So this means in particular, right, this implies that phi k lambda k is smaller or equal than sum over j from 1 to n of just m I max j. Right, but these numbers are all negative. So if having absolute values or not is the same, and we know that they sum to 1. Right, so the proof is done. Right, we know, and of course there's some absolute values. Right, so in absolute value, lambda k is always smaller than 1. So in particular, it means the biggest one is equal to 1, and we can take the first eigenvector to just be the whole ones vector. So what this means in particular, it means that the first coordinate of the diffusion maps, or this embedding that we're defining, is not really interesting because it's sending all of the vertices to the same coordinate in that dimension. And so we can ignore that, and we can have diffusion map. Right? We can send node I. Now node I can be sent to, right? We can start at 2, lambda 2 t phi 2 at node I, lambda 3 t phi 3 at node I. Okay, so now we've already improved a little because now our dimension, right, d is equal to n minus 1. So we gained 1 dimension, it's not a lot. It's a start, but it's not a lot. But now how can we do further? How can we go further? Right, think of t, right, as t grows, right, we can take t to say be 10. I mean, in practice, when you're given a data set, you have to pick some t. But as you see, it doesn't really matter because t now, because of the way the spectral decomposition works, the dependency on t will just shrink and expand each dimension. It won't make the dimensions interact with each other, right? It will just expand or shrink the dimensions. If you look at what happens in one dimension, they'll still be exactly the same way, just maybe shrunk or expanded. And so now, right now, if, let's say, now, as we take t very large, the ones that are the lambdas that are close to 0 are going to matter a lot less. Right, so most of the energy of this embedding will come from things that are very close to 1. And so in particular, it would be nice, like, what our potential problems are. Okay, so we know that these are ordered from biggest to smallest, so there's 1 at 1 that we took away, maybe say this is 0.9, 0.8, and so on. The problem is that they might have negative eigenvalues, right? It could be that, that there are negative eigenvalues. So it could be that this is a very, say, large negative number, like -1 or -0.9, and so in absolute value, it could be bigger than one of these. Okay, so potential problem, they could be large, so lambda n could be, say, very close to -1, right? And so a lot of the contribution is coming from the bottom. And in fact, we know that this is also a very nice homework problem to think about, that lambda n is equal to 1, essentially, if and only if the graph is bipartite. Right? This is a very nice thing to show, that you can see properties like bipartiteness and properties of the graph also on the other side of the spectrum. Now, one way to remedy this, right? Because if you think about heat diffusing or a chemical or something, like a bipartite thing doesn't make much sense, right? The -1 eigenvalue means that things are jumping like plus, minus, plus, minus, plus, minus as t grows, right? Because you get to square, the even powers are positive, the odd powers are negative. And you don't expect sort of heat diffusion to go that way, right? Because it doesn't make sense that you have two things, and heat at odd times is always here, and at even times is always there. And why? Because heat also stays a little in the place where it is, right? It doesn't all go away. So one solution, right, and this is what I do if I have to deal with any kind of data set, is I consider a lazy random walk. Right, and the lazy random walk is you add some probability, right? So you add some probability of staying where you are. Right, so the idea being to add probability of not moving. Right, one potential way of doing this is you just take a new m prime to be, say, half identity plus half m. Right, so now you're saying take a step, right? Take a step, only with probability half. Right now, for sure, for this n prime, right, the lambda case of this n prime, right, they are just a half plus a half of lambda case. So in particular, of course, we still have that n1, lambda 1 of m prime is still 1. But now we know that all of them need to be between 0 and 1. Right? If they were minus 1, they become 0. If they were 1, they stay at 1. So now they're all between 0 and 1. And so we can, so that without loss of generality, we're going to assume that all the eigenvalues are bigger or equal than 0. Right? And usually when I get a data set, if they're not bigger or equal than 0, then I just make the random walk lazy and say this way. Right? I just take instead the lazy random walk. Okay, so let's assume that the eigenvalues are all 0, are all bigger or equal than 0. Okay, so by taking by making the random walk lazy, let's assume we can have all we can have. Okay, we have all the eigenvalues being bigger or equal than 0. Now that all the eigenvalues are bigger or equal than 0, then we have something very interesting, right? Because what we have is that they're all ordered also by magnitude. Right? All these eigenvalues become ordered by magnitude. So in particular, the energy comes a lot more from these, and these start being a lot smaller in magnitude. Right? So these become ordered also by magnitude. And so it makes a lot of sense. Most of the energy of the embedding is going to come from the first few coordinates, the first few eigenvalues and eigenvectors. So the idea is to do the so-called truncated diffusion maps. And the truncated diffusion maps are the following. Right? They are node I, so let's give them a name. Let me make sure I use the same notation. Right, so they'll be at the time t, and for a node I, for a truncation d, because we're going to send them to dimension d, right, of a node I, right, is going to do, or let me map it this way, right, this is going to send node I, right, sometimes we call this bi, to the truncation of that map. D plus 1. Now, the really cool thing about this is that, well, okay, one very nice thing is that now this lives in the right space. Right? This is in RD. This has now most of the energy. Right? This will have now most of the energy. Right? Because we know the eigenvalues after, say, d plus 1, they're smaller. When I take a power t, I'm making them, right? I'm making them in particular smaller. And this means in particular that, you know, spectral clustering, now if you think about what spectral clustering is nothing but taking the truncated diffusion map, right? Maybe at t equals 0, so that these terms don't show up, and then using k-means. So spectral clustering, right, after we do this, then really spectral clustering, right, is nothing but k-means on the diffusion map at dimension, the truncated diffusion map at dimension k minus 1. Right, instead of times 0. And so, but what we'll see in the second part is that not only this allows you to cluster, but it will actually allow you to visualize the data. Because if I take, right, if you take, say, d equals 2 or d equals 3, we can visualize. Right? We can see the data. Right? We can see the data in the computer, say on computer screen. Right, so we can see the data, and in the computer screen, this is exactly what I'm going to do now. Okay, so maybe in 2 dimensions, in 3, you can see it on the computer screen and move it around. Now, there's a few things we can show about properties of diffusion maps. So, in particular, right, we did this thing where we wrote it. We had this mapping of the probability clouds. And we wrote the mapping in these coordinates of psi t, but psi t itself is not an orthogonal system, right? It's not an orthonormal basis. It is part of a biorthogonal system, but it itself is not an orthonormal basis. And so now you can ask, okay, but now if I look at the distance between 2 points in the diffusion map, right? I look at this embedding, let's say I don't truncate, and then I'll look at the Euclidean distance between these 2 points. Is this actually in any way interpretable with respect to distances between the probability clouds? And in fact it is. One can show, and this is in the notes, that the L2 distance between the diffusion maps, right, is the same as, so the Euclidean distance, the same as the L2 distance between the probability clouds with the weight on each node depending on its degree, right? There's a particular weighting, but they are related. Now, of course, for the truncated one, it depends on how fast you have a decay of eigenvalues, right? But if you remember also PCA was very much of this type too, right? You wrote it in some, you can think of it as writing it in some spectral bases and then truncating at some point and eliminating the last eigenvalue. So all these like elbow method and all these things to try to predict what are the, where to cut off the eigenvalues, you can do it here. And then there's also a big, there's also very similar to how you can think about what eigenvalues do for in the matrix and so on. You can now think, what do these eigenvalues look like from other types of data? So you can think, for example, if you sample a manifold like a surface, or these half moons that I drew at some point, right? Maybe a set that looks like this, right? Some kind of manifold. And then I do diffusion maps and I look at the eigenvalues. Can I say something about the eigenvalues with respect to that? With some eigenvalues of some operator there. And right, heat is sort of described by the Laplacian type operators. And one can say that if you sample from something, then the eigenvalues, right, after the 1 minus or potential laziness and so on, will converge in certain place to the eigenvalues of the Laplacian. And the eigenvalues of the Laplacian, you can tell you a lot about the manifold. And from the manifold, you also, of course, know a lot about the eigenvalues, and they should start getting smaller at some point, and so on. In particular, this question in, I guess, differential geometry of what can you tell about the manifold, about your data, given eigenvalues of this type, or of the Laplacian, and so on, is what people often times call can you hear the shape of a drum? Right, where the drum is the manifold or the surface, and hearing the shape is looking at eigenvalues in a certain sense. And so, questions from the eigenvalues: what can you say about the shape of the drum? And this is a very interesting problem in differential geometry. And so, in the second part, we'll look at some examples of data to see what the graphs look like, and what the visualization that diffusion maps gives us. What does that look like?